Hey everyone, if I didn't get a chance to say good morning as you walked in, good morning. Welcome back to another day of calculus, this time a virtual edition. Continue us on the journey through our portion of the conversation of area when it comes to integrals in calculus. In the last session, we talked about using rectangles to approximate the area under a curve. I didn't state explicitly what it was called, but this is called a Riemann sum. It is actually after Bernhard Riemann, who was a German mathematician. He realized that the idea of breaking up regions under curves wasn't entirely new to him. He could break it up using geometry, just like we had talked about, using things like rectangles, triangles, and trapezoids. He focused strictly on the rectangles themselves and realized that the more that he used, of course, the better the approximation would be. We know that this is really just limits behind the scenes. The thing getting really, really big is the number of rectangles that he's using. The thing that's getting really, really small is the amount of error between his calculation, the approximation, and the exact value of the area under the curve. In our last session, we talked about approximating three different ways: right hand, left hand, and midpoint. So as a refresher, in example 3, we said that this one was going to be an under approximation because you can see all these regions in pink are being underestimated. So in this case, this was a right-handed. If you're looking at the data points, you could see that the right-handed points of all the rectangles for their heights is determining what the height will be. On the other side of the coin, if we do things left-handed we know in this case will produce an overestimate. If you look here in light blue, you'll see that the rectangles themselves are going past the curve. And then we did say that midpoint was kind of the best of two worlds. If you over approximate a little bit and under approximate a little bit, they'll end up canceling each other out. So like you can imagine, like this region here would fill in with this region and would then make it a lot more accurate. So in general, I would say left hand, right hand is not bad, but midpoint for sure is the better of the three options. So move on to example 4. Today we'll spend a little bit more time doing these Riemann sums. Again, Riemann sums credited to Bernhard Riemann, a German mathematician, and that's the reason they're called that way. If you see something ask you to calculate the Riemann sum, it's just really asking you to approximate the area under a curve using rectangles. So for this one, it says use 4 rectangles to find upper and lower sums of the area for the region for x squared and the x-axis between 0 and 2. Upper and lower sums are going to be like the overestimates, underestimates. Just by the look of it, let's say we're looking at this one to kind of start, you can see that the left end points are kind of determining the height of the rectangle. Even this last one here is going to be determined by x equals 0. So let's do this as a left-handed. We do know that left-handed in this case is going to produce an under approximation. We can see that there's going to be a decent chunk of area that's missing, and that's okay. So for an under approximation, the first thing I would tackle is finding out how wide each rectangle would be. We know, after all, the length times the width is the area of a rectangle. So to do this, I calculate delta x over n. So delta x is the change in x. So in this case, the interval is from 2 to 0, so 2 minus 0 over n. How many rectangles do I want? Which in this case is 4. 2 divided by 4 is going to be a half. So in this case, I want every rectangle to have a width of 1/2, and that is the part of the calculations that's going to stay consistent. Anytime that you're doing this, you want the width of the rectangles to be the same, but we'll see at the end of the conversation today that there are some cases where you have to kind of run with not having the same width rectangles if the information is provided to you in a certain way. But for our purposes, we can say each rectangle is going to have a width of 1/2. So underneath here, just to give myself some space to write. So we'll write in kind of a formal way. What are we doing? We're integrating. We're finding the area of the curve from 0 to 2 of a function. In this case, the function is x squared. You could also write x squared there. We know it's an approximation, so I'm going to go with these squiggle lines. If I know that the width of every rectangle is going to be 1/2, I can pull it out as kind of like a common factor. And now I'll start the process. Left-handed, where should it start from 0 to 2? It should start at 0. I want to find out what is the height at x equals 0. The next one that I'd be interested in is the height at 1/2. The next thing would be the height at 1, and then the height at 3/2. In terms of calculation, this is not too terrible. We know that we're just squaring these quantities, so we could use a calculator, but I'm not sure that it's necessary, right? 0 squared is 0. 1/2 squared is 1/4. 1 squared is 1. And then 3/2 squared is going to be 9/4. If you then take this into your calculator, 1/2 times this quantity, if you add them together, you're going to get 1.75. Inside of these brackets is 3.5 if you add it together. So in this case, I could say the left-hand approximation, which is the under approximation, is going to be 1.75. Feel free to pause the video if you want to double check that using your calculator, or just pause the video to go back and look at anything else or revisit something I've already said. So what if we tackle the same question, but now notice we're using the right endpoints to kind of determine the height of the rectangles. So this one we're going to do right-handed. For our purposes, we do know that the delta x over n is still going to be 1/2. For these examples, they kind of stay the same. So let's attack it. So in this case, I have the integral. We're going to go from 0 to 2 again of the function dx. I know the height of each rectangle is still going, or the width is still going to stay as 1/2, but now heights are not going to start at 0. If it makes sense to you, the first one I'm going to have is going to start at x equals 1/2, and then it's going to go to 1, and then it's going to go to 3/2, and then it's going to go to 2. So let's reflect that just by using the notation. And after a while, if you get good at this and you don't feel like this step is necessary, that's completely fine. I'm in charge of the explaining, so I'm going to show the steps just in case we have somebody that's not sure where it's coming from. Again, just squaring these quantities is not a terrible thing in terms of the function itself. So we know that, again, 1/2 squared is 1/4, 1 squared is 1, 3/2 squared is 9/4, and of course 2 squared is going to be 4. If you take this into your calculator, you'll find out this is 3.75. If you want to double check it, the inside of the brackets, this quantity is 7.5. Half of 7.5 is 3.75. So in this case, I did also forget to mention it's going to be an over approximation. We can tell from the curve itself that this is going to be too much area. So where the first one was lacking some, right, so it was missing some of the area, this one maybe had too much. Classically, you would think an average would be in line, which an average would be a good idea, but because the graph has curvature, because it has concavity, we know that we're not expecting the midpoint to come back exactly as the average of the left hand and the right hand. So speaking of midpoint, let's take a second to look at it. Of course, here for midpoint, we can see, similar to what I've said on Friday and what I said already here earlier in the video, is that the beauty of the midpoint is that it does a kind of a partial over approximation and a partial under. And you imagine if that part fills in, the over approximation fills in for the under approximation, then it actually ends up being pretty close to exact. So let's build something for midpoint. In this case, the delta x over n is still going to be 1/2. We do know that midpoint is going to be relatively more accurate than left hand and right hand, so that's a good thing. So let's just build an integral. Again, we're still going from 0 to 2 of the function. With respect to x, we know it's an approximation. I'm going to use 1/2 as the width of every rectangle that doesn't change. But now you got to kind of think that we're doing the halfway points for each interval, right? So from 0 to 0.5, from 0 to 1/2, we know that that's going to be 1/4 or 1/4. So the first x value that I want the height at is going to be 1/4. And then I can really just add 1/2 to that going down the line. So if I take 1/4 and add 1/2, that's going to be 3/4, then 5/4, and then 7/4. Also not terrible because the function itself is still just squaring it. So I'm just going down the line. 1/4 squared is 1/16. 3/4, 9/16. 5/4, 25/16. And 7/4, 49/16. If you add everything up in that quantity, I got 5.25, and 1/2 of that, 5.25, is 2.625. So then if you look a little bit closer to what I have here in terms of the picture, you'll see that there's like the estimated area. So there's like this little yellow rectangle. And if I just go back down the line real quick, right? So 1.75 was the estimated area, but the actual area was 2.67 for left-handed. For right-handed, 3.75 is what we got. The actual area, 2.67 or 667 if you go 3 decimal places. And if you look at the midpoint, you'll see that's the closest of the group. We got 2.625. and the actual area is 2.667. So we'll do one more example, and then I'll actually show you how to use the calculator to find the exact value of the area. So that way, if you want, you can kind of check to see how the approximations are going and how they compare to the exact. Coming very soon in our conversation, how you can actually find exact by hand. We know this is kind of how classically calculus and math is taught, right? So you kind of have the longer clunky way, traditionally, how did it start? And then we'll get some shortcuts and we'll be able to show you how to find it exactly without such a tedious method. But it's a good place to start and definitely a good place to begin the conversation. All right, so how about example 5? Use 5 rectangles to find upper and lower sums of the area for the region lying between the graphs of x cubed, the x-axis, and the vertical lines 0 and 2. So we will do upper and lower sums. In this case, let's just find out which one is going to be the over approximation, under approximation, and we'll probably leave the midpoint out of this one. So how about just by looking at the picture? If you're looking at the picture, can you determine which one's which? Can you determine what handedness would produce an over approximation, under approximation? So just by looking at the picture, you can see that this is going to be right-handed, and it looks like right-handed produces the over approximation. My dog Watson is spinning in circles, so if you hear him, he wants my attention, and I'm doing the video. All right, Watson. All right, so away we go. 5 rectangles for this function. So maybe just kind of looking at it, we can say the upper in this case is going to be the over approximation. And that's going to be with right-handed. We know the lower is going to be the under approximation. And that's going to be left-handed. I'd also want to know what is the width of all the rectangles. So taking delta x over n, we know the regions from 2 to 0, and we know that we want 5 rectangles, so I think it will be 2/5 as the width of all of our rectangles. So just going right to it, so let's start with the right-handed. So I know right-handed is going to produce the over approximation. So again, just using the notation from 0 to 2 is the integral for the function with respect to x. 2/5 as the width of all the rectangles, and then just going down the line. If I look at it right, I wouldn't want to start it at 0 because I know the first rectangle would be from 0 to 2/5. So since it's right-handed, I want the first y value, the first height of the rectangle to be at 2/5, and then just every subsequent 2/5 after that. So then the next one will be 4/5, the next one 6/5, the next one 8/5. And of course, the last one just at 2. So then if I take these into the function itself, I've got to cube each one of them. I went ahead and just did this using the calculator. For this inside region, inside the quantity, I got 14.4. And if I take 14.4 and multiply by 2/5, I got 5.76. I do know that 5.76 I'm expecting to be the overestimate. I'm expecting to be too big. So then what about at the same time if I tackle the left-hand side? Not a huge difference, right? In this case, I'll go from 0 to 2. The function with respect to x, I know the width of the rectangles will be 2/5. But now because I'm doing this one left-handed, hopefully it would make sense that we're going to start it at 0 since that's the farthest left I could go in the interval that I'm interested in, and every subsequent 2/5 after that. So then f of 2/5, f of 4/5, f of 6/5, and f of 8/5. If I then take that entire region, I got 6.4. If you want to double check it for yourself, 2/5 times 6.4, I got 2.56. So maybe in the notes you could say this guy is what you're expecting to be the over approximation, and this guy is what we're expecting to be the under approximation. All right. So that kind of completes it with the upper and lower sums. Again, upper and lower, just another way of saying over approximation, under approximation, left hand, right hand. But I did tell you I was going to show you how to use the calculator to find this area exactly. So I'll actually show you how to do it for x squared, and then you can try it for this one, which is for x cubed. So going back to example number 4, just so you can see how did we get to this 2.667. You can take your calculator. Let's input x squared as the function itself. Again, I'll do it for x squared, and then you can try it for x cubed. So reset your calculator, maybe make sure it's like zoom 6 so you have a nice standard window. Once you sneak in x squared, we'll zoom in a little bit. So put an x squared into your y equals screen, then go to zoom, number 2, zoom in. On the origin, press enter, so then it will kind of blow up your parabola a bit, make it a little bit bigger. And then the keystrokes are going to be to hit second, which is in the top left of your calculator, and then trace. When you hit second trace, you'll recognize some things that we often use in Algebra 2, and often we've also used in our class, things like the minimum, the maximum, the intersect. But if you now look at number 7, you'll say now number 7 actually has quite a bit more meaning to you. It is the integral of the function with respect to x, of course notation being rather important. So go ahead and press number 7. When you press number 7, it will take you back to your graphing screen, and it will say lower limit. When it says lower limit question mark, you want to say what is the lowest value of x that you want to start your interval for collecting area. For us, we know that the x value is going from 0 to 2, so go ahead and put x equals 0. So I think you just put in 0 and you press enter. Once you put 0, enter, it will now ask you what is the upper limit. Of course, the upper limit for us is going to be 2, since that's where we want to stop collecting area for x. So go ahead and put 2 and hit enter. And when you do it, you will actually see your calculator span out to the right and then collect area, and we'll actually shade it in. So if you're looking at your calculator, this region right here is actually the exact area under the curve from 0 to 2. And if you look at what it says here, this is where the 2.667 came from. And I did mention that coming soon we are going to tackle it together, where we actually show how you can do this by hand and get an exact answer rather than the approximation. Very similar to for derivatives. If you remember, we had the limit definition and derivative that took quite a good amount of time in algebra, but then eventually that became the power rule, and the power rule is now something a lot of people do very, very quickly, which is great. So I'd have you try the same thing for x cubed. So if you want, take a second there on your calculator, pause the video, reset your y equals screen to x cubed, maybe reset the window so you could see x cubed, maybe from 0 to 2. And if you pause the video, I'll give you a second to do it for yourself. Otherwise, I'll just keep going so the video doesn't last forever. So when I did this in the calculator myself, I went from 0 to 2 for x cubed and then dx. We now don't need the squiggly line. We can say equals, and we have it equal to 4. So then in comparison to the other two that we had, if you took a look at the right hand approximation was supposed to be, for us, 5.76, which was the over. The left hand was the under approximation. It was 2.56. In this case, 4 does find itself somewhere near the middle, but neither one is very good, right? It's left hand, right hand. How can we make it better? Well, how about instead of just 5 rectangles, what if we did 50? What if we did 100 rectangles? Of course, by hand, that becomes rather tedious to write out, so we kind of stick to a small number of rectangles, but if we wanted the approximation to be better, there are ways that can make it better. So at least now in your calculator, you know a way that you can double check it and see how your approximations are doing. All right, so now it will be time for the assignment. This meme itself is kind of hinting at the fact the next thing we should talk about is trapezoids. So tomorrow's video will be about doing these approximations with trapezoids. It turns out rectangles are good, but trapezoids in some cases are actually significantly better. So if you go to your assignments, if you flip over in your notes, you're going to see an assignment that starts with this question right here. I still want to do one more question with you just to kind of give you a flavor of what these things would look like. But if you look at a little note packet I gave you, there are some worksheets in there. Look for question number 1 where it has this table that goes from -5 to -3 to 0 to 1 to 5. You can pause the video to see if you can find that. So I'm going to do this extra question. This one is not in the packet. This one's not in your assignment, but at least it's a good one to talk about. So very similar to the first one you're expected to do on the paper. It gives you a table. It goes 2, 5, 10, 14, and it says the function f is continuous on a closed interval from 2 to 14 and has values as shown in the table above. Using the subintervals from 2 to 5, 5 to 10, 10 to 14, what is the approximation of the integral from 2 to 14 of a function dx by using a right Riemann sum? So first thing, a right Riemann, again I told you Riemann sums credited to Bernhard Riemann, German mathematician who came up with the idea of approximating areas using rectangles. What is all the subintervals? This is actually telling you where the rectangles are going to be. So looking at this, we can say from 2 to 5, that's going to be my first rectangle. From 5 to 10 is the second rectangle, and from 10 to 14 will be the third rectangle. So you can imagine you're doing this with 3 rectangles. The only issue that starts to arise is if you start to do it, so we know we want to do width times height. We know that the y values, f of x, is going to be what we're using for the heights. We want it to be a right Riemann sum. And then for x, we know this is going to kind of serve as the width. So let's write some notation. Okay, you don't necessarily have to write this one down since you have the video to look back at if you wanted to. So looking at notation, I want to take this integral, I want to approximate it using these rectangles. But if you look at the rectangles themselves, from 2 to 5, you'll notice that this is a change in x values of 3, so that would be the first width. But if I do the next one from 5 to 10, that would be 5 for the width, and the last one from 10 to 14 would be 4. So where in the previous examples, when we have the function, we always try to make the width the same. In this case, we have to run with widths that are not the same because we don't have the function itself. We just have certain snippets of the x and y values. So I'm just going to go rectangle by rectangle. For the first one, we have a width of 3 because the difference from 2 and 5 is 3. But now I have a choice. Do I want to go with the y value of 12 or y value of 28? Since this is on the left side and this is on the right side, we're going to go with 28. So in this case, it's right-handed. It's a right Riemann sum. So 28 plus, I now scoot over to my next rectangle. The next rectangle has a width of 5 because the x values are changing by 5. And if I look at it here, my choices are 28 and 34. In this case, 34 is the right-handed one, so I'm going to go with 34. And then plus, the last rectangle has a width of 4. And if I'm looking at it left hand, right hand, it looks like the height I'm going to be running with is going to be 30. So just going down the line, 3 times 28, 84. 5 times 34 is 170. And 4 times 30 is going to be 120. If you add these guys together, you're actually going to get 374, which is going to be letter D, which is going to be my answer. So if you think about it, it's actually not too terrible. It's just taking the idea that we talked about. This is actually an old AP question. They often ask this in like the no calculator part of the AP exam because multiplying and adding these numbers is not terrible. And then without having to go to the calculator, find all these extra y values, this would be a very quick way of checking your understanding. So I think that will help as like an example for the ones I'm going to ask you to do. So going back to the assignment, your assignment for today are these 4 questions. So number 1, notice how it does it with left, right, midpoints. That would be a good conversation for you guys to have. And then this one's kind of interesting. Question number 2, can you tell me which one's which? Just depending on whether you can say some things about the function. Can you tell me for the 1.345, 1.578, and 1.723 over approximation, under approximation, you'll then see that there's an application to physics. Here it says approximate the distance she traveled. So notice here they give us kind of the velocity graph. So as a hint, maybe we can say the integral of v of t dt. The area under the curve for our velocity time graph will be the total distance traveled. If you remember, this is actually an old conversation that we've had. I think it's actually even a conversation that we had last week at the end of the week. So just use the midpoint approximation, and when you find the midpoint approximation for the integral for a velocity time graph, that will be the total distance traveled. And then if I could give you a hint for number 4, I would say use different colors. So notice here for part A, there's right, left, midpoint, and also a graph to kind of help you do this. Now, I will tell you the graph is not exact for some of the y values, so everyone's going to have maybe slightly different y values. Just try to approximate as you can. But for maybe each different part, use a different color. That way, when you're doing them all in the graph, and yes, I am going to ask you to sketch here on the graph, then maybe the colors will stick out to you. So maybe do the first one in letter A in blue, let B in red, and maybe C in pencil or something like that, just so you could see it. And I would recommend maybe doing each one kind of in pencil first and then going back over it with a color, just in case you make a mistake. I don't want you to have to permanently change it or mess up the picture. The picture is supposed to help make it easier to understand. All right, so there is an answer key on Canvas for this 4-question assignment. So as you're doing it, if you want to kind of check to see as you go to make sure that everything's going right, then just pull up Canvas and take a peek. All right, well, let me know if you guys have any questions, and good luck with it. I'll see you tomorrow for the next video on trapezoidal rule. All right, guys, good luck and have a great day.